We can design an instance where it will inspect all the leaves. Remember that we do worst case analysis, that we take the worst instance. Okay, so in the case of a deterministic one, we can construct a specially designed instance for this algorithm where it will inspect all the leaves. So it's just a twist over the deterministic algorithm. It's just choose the first one we evaluate randomly. And because it's random, the algorithm, the adversary cannot design a very bad instance. Okay, it can just design some bad instance, but not very bad ones. It cannot force us to expect all the leaves.
Assuming he doesn't know
Oh yes, of course. If he does know the random bits, it's just a deterministic algorithm now. Okay, if the adversary knows the random bit, the algorithm is no more random. It's deterministic algorithm. Okay, because since when you fix the random string, then it's just a deterministic algorithm that reads the string and the input. So it's a deterministic algorithm. Okay, so that's very important that the adversary does not know the random bits. If he knows the random bits, it's just the same as if the algorithm was a deterministic one. Okay, so maybe you're right. I think you should study it and tell us. Good. Okay, so now we have a huge improvement over from n. We went to n to the 0.7, and this is a big improvement. Okay, because if n is 1 billiard or whatsoever, you may just have instead of inspecting 1 billiard nodes, you just have to inspect, I don't know, 10,000 or something like that. So it's much better. Okay, it's a polynomial gain. Good. So now the question is, and was raised there, is how good is it? Is it the best we can do? Okay, is it the best we can do? Can we show that we cannot do better, or at least can we get some bound on the minimum number of leaves that a randomized algorithm needs to inspect? Okay. So that's exactly what we will try to show, and we will get some lower bound that will not match this one, maybe because it's not tight. Okay, but also maybe because, surely because it's not the best we can do. And what we will use is a very powerful thing and a beautiful one that also comes from game theory, which is quite funny, which is named Yao principle. Okay, so Yao principle is a way to get lower bound on randomized algorithm. This way is really funny in the sense that it's pretty impossible to tell it correctly, so I will try to do it. So what does it say? What does it say? It says the following, is that the cost of the best randomized algorithm on its worst instance is at least, and in fact it's equal, but we just need at least, but in fact it's equal, okay? The expected cost on the expected cost of the best deterministic algorithm for the worst distribution of instances. Oops. Okay. So the cost of the best randomized algorithm on its worst instance. Okay, so you look at all the randomized algorithm. For each of them, you look at their worst instance. Okay, and you take the one with the lowest expected cost. Okay, this is exactly what we are looking for. Okay, we are looking for the best randomized algorithm in its worst case. Okay, this cost is at least the cost of, you look at all the distribution over instances, and for each of them, you look at their best deterministic algorithm. Okay? Then, this thing is less than the cost of the best randomized algorithm. So basically, what does this mean? There is somehow a transfer of randomness from the algorithm to the instance. And how does it help here? Is basically, you just have to find a bad distribution of instances. If you find a bad distribution of instances and are able to show that any deterministic algorithm will take at least this time to solve this instance, this distribution of instance on expectation, then you know that this value is a lower bound on the cost of any randomized algorithm. Okay? So, let's see how this works. Let's see how, the nice thing is that it is tight. Okay? Equal, in fact. But that means it's a very powerful principle. That means that you really have a tight equality. So basically what can you show is that basically if you can find an algorithm whose cost equals the cost of some deterministic algorithm over of the best deterministic algorithm over some distribution, then you know that your algorithm is optimal. Okay? So how do you prove that? It's a two-line proof. And basically, the hardest part is to read the principle and try to understand it. Once you have it, it's really easy to prove. Okay? So let's see how to prove it. It's a two-line proof, but it's hard to write. Let's see if I can do it. So, how does this work? So for the ones who know zero-sum games, it's a direct corollary of von Neumann theorem, von Neumann minimax theorem. So where does it come from? So the proof is really easy. So we focus of instances of size n. Okay, so we look at instances of size n. Okay, and we look at all the possible algorithms for this instance. Okay, so there is a finite number of algorithms that will inspect. There is just simply in which order do you inspect the leaves. Okay, so there is a finite number of algorithms. Okay, and these are here. Here you put the algorithms. All the deterministic algorithms. Okay. So here you put all the deterministic algorithms. Okay, so you just consider instances of size n, okay, and algorithms, deterministic algorithms for instances of size n, okay? So you put the deterministic algorithm here, and you put the instance there. So you number the instances from 1 to something. Okay, here it's 1 to 2 to the 4 to the k, 2 to the n, 1 to... So in our case, it's from 0 to 2 to the n minus 1. Okay, and the algorithm from something to somewhere. Okay, I don't know, some big number. Okay, and what do you put in the matrix here? You put here the cost, that is to say the number of leaves inspected by algorithm I over instance j. So the only thing that we look at is in which order the leaves are inspected. Okay, so this is what we call an algorithm. Okay, we just look at these algorithms are deterministic. Okay, so depending on the value of the leaves, they will inspect. There will be a branching process. Okay, but it's there are at most 2 to the 2 to the n factorial or whatever, but it's a finite number. Okay, but in fact it doesn't matter whether it's finite or not. We don't care. But the only thing here is that it's finite. Okay, so we put it here. So now we will try to evaluate what does this mean. What are the words in Yao principle? How they are related to this matrix? Okay. So let's start with the easy part. So we look at a distribution over the instances. Okay. What is a distribution over the instances? So the distribution over the instances is simply a vector Q. Okay. A distribution over the instances is a vector Q, okay, which is positive, and such that the sum over all the instances of the Qj is equal to 1. Okay, this is a distribution over the instance, Qj, okay, it's the probability that the instance is ij. Okay? So, now we take a distribution Q of instances, okay, and we look at the cost of the best deterministic algorithm. Okay? So, what is that? What is this thing here? This thing here is for the worst distribution. So it's the max over Q, okay, of the best, the mean over all the deterministic algorithm, I, okay, of what? Of the expected cost over Q of AI over instance J, where J is, let's say that J is chosen randomly according to Q. Okay, so let's say that, let's write it this way, okay, where J belongs randomly, it's chosen randomly according to the law Q. Okay? What is that in terms of the matrix coefficient? It's simply the sum over all the instances of, with probability Qj, I choose the instance J, and in that case, my cost is the cost of AI over instance J. Okay? So if this matrix, let's call it matrix C, okay, this is simply the sum over J of Qj of Cij times Qj. This is exactly C times Q. Ci times Q, where Ci is the ith row of C. Is it clear for everyone? What is the cost of this algorithm for some Q? It's simply this row vector here, which is all the cost of AI over all instances ij, times the distribution over the instances Q. Okay, so this is row Ci, okay, and this second part of the algorithm is the max of the principle is the max over Q of the mean over I of Ci times Q. Okay? It's yeah, expected. Simply the expected is the sum over all instances of the probability that this instance is chosen and times the cost of the algorithm for this instance. And this is Cij. So this is the sum over j of Cij times Qj, and this is, by definition, exactly the product of the row vector Ci times the column vector Q.
But the expectancy over all instances.
Yes, but Q tells you, Q is the law according to which the instances are chosen. Okay? So let's now look at the other part of the principle. What is the other part? It's the cost of the algorithm on its worst instance. So you're looking at the best randomized algorithm. So the best, so let's call it AP, okay, for a moment, and let's see what I mean by that. Okay? Over the worst instance, so the worst instance is the maximum J of the expected cost of AP over Ij. Okay, so I look at all the randomized algorithm. I take its worst instance J, the one that maximizes the expected cost according to P, according to the expected cost of a randomized algorithm AP, on this worst instance. Okay? And then I choose the best randomized algorithm. Okay? So now, how this quantity relates to my matrix here. The question is, what is a randomized algorithm? What is a randomized algorithm? Remember that a randomized algorithm, it's a deterministic algorithm, okay, that reads two things, the input, okay, and the random string. And a random string. Okay? But once the random string is fixed, the algorithm is deterministic. Okay? So the algorithm for a given R, random string R, this algorithm is it's AR. Okay, for a random string, it's AR. Okay, so basically, what is a random algorithm? A randomized algorithm is a distribution over deterministic algorithm. Okay, a randomized algorithm is a distribution over deterministic algorithm. You choose a random number and it gives you a deterministic algorithm. Follow me? Okay, so what is it? It's simply a vector P such that Pi, is the probability that the algorithm is running AI. Oops. Is it clear with you, or?
Do you consider the size of the algorithm? Because if you add a random string with the algorithm, the size.
It doesn't matter whether it's finite or not. Okay, that's the point. Okay, I agree with you that there is an issue, but again, since there is a finite number of algorithms, a finite number of way to inspect the leaves, maybe you will have a finitely many times the same algorithm, but at the end you will end up with some fixed probability for each of them. Okay? But anyway, it doesn't matter whether the matrix is finite or not. Let's assume it's finite for now because it makes things easier, but it doesn't matter. Okay? So, a randomized algorithm is simply completely determined by the vector P here. So, now let's do the same thing here. What is the expected cost of AP here now?